So let's move on. Let's now discuss the total stress tensor. Okay, so previous class we were talking about the stress vector and stress tensor with respect to solids. Now we'll get back to fluids. Okay, so for fluids, the total stress tensor, which is represented as capital T, has both static and dynamic contributions. Okay, now all our previous discussions on stress tensor tau for solids is simply extendable to capital T for fluids, irrespective of whether it is flowing or not. And okay, so this is something that we already know, and it's the Cauchy's law. So simply in place of tau, previously which we had written tau, here we have replaced with capital T, total stress tensor components. Now the properties of these components, again you can see these are very important actually. Shear stresses acting on opposite sides of an interface at a point are equal and opposite, and the same applies to normal stresses. Okay, and the second property is cross shears, like for example tau yx and tau xy, they will be equal on adjacent faces at a point. And well, these two properties would also imply that the total stress tensor is symmetric. This is very important. All right, moving on. So okay, so we are coming back to fluids from solids, right? It is important to understand what's different over here. So the solids actually would resist shear stress under a static condition. However, fluids, if you see, they cannot do so. However small the shear stress is. Okay, solids they tend to reach they will reach an equilibrium stage after some time. Okay, and they'll stop deforming. However, that is not the case for fluids. They'll just flow. They'll deform continuously. And solids, you see, they can regain their original shape once the force is removed. However, fluids they just cannot come back to the previous configuration. And for solids, the force that is acting upon it will depend on the deformation. However, here the force on fluids would depend on the rate of deformation. Okay, these are important differences to be kept in mind. We'll move on. Okay, so as we saw, fluids cannot sustain a shear stress, and thus what we do is the shear stress components in the total stress tensor will go to zero, and thus the total stress tensor, if you can see, is diagonal. That and from Cauchy's law, we can write the stress vector for any surface with the normal vector n as shown. And of course, if there's only normal stress, then the stress vector will be parallel to the normal vector, right? And therefore Tn is equal to some lambda into n. Now we'll compare components, and what we'll get is Tx is equal to Ty equal to Tz equal to lambda, and this lambda will be equal to minus p in case of static fluids where p is the pressure. And the magnitude of the stress vector in this case, okay, in the static case, is independent of n of the normal vector, whatever direction it is, because it is simply equal to the magnitude of the pressure. All right, and the total, of course, total stress is now pressure stress plus viscous stress. All right, and therefore we can write T is equal to minus P into I plus tau, where this I is the identity matrix, and this is tau. Now this tau is the viscous stress tensor, and thus for fluids in general we can write the total stress tensor as shown below. Okay, minus P plus tau xx, tau xy, tau xz, and so on. Moving on. Okay, so this is picture will simply explain whatever was shown in the previous slide. Very good representation. So this is the pressure stress and viscous stress and total stress, as you can see. Moving on. Okay, let's of course get back to our aim of completing the linear momentum balance in x direction. So we were in search of the net surface force terms, right? So the net surface force in x direction due to pressure is P into delta V delta Z minus P into delta V delta Z. This is evaluated at x, and this is at x plus delta x. Once again, as you might have guessed it, we are considering the small cuboidal control volume, right? Delta x, delta y, delta z as the sides. And the net surface force in x direction due to viscous stress will be as shown below, and you can clearly see this in the image here. All right, so this is the pressure. As you know, it is compressive. So P at x delta y delta z minus P at x plus delta x into delta y delta z. That will be the net pressure force acting in the x direction, and these are all the viscous stress forces acting on the control volume in the x direction. You can have a look at it. Fine. And all of these terms will add them up and divide by delta x, delta y, delta z, and of course shrink the control volume to a point, and thus we'll get the surface force term per unit volume, right? So minus dou p by dou x plus dou tau xx by dou x plus dou tau yx by dou y plus dou tau zx by dou z. As you can see, the second subscript here is x because we are conserving momentum along the x direction. So hence linear momentum balance along x direction is written as, we already have seen the left hand side, and now we can complete the right hand side. Rho gx is something that we already knew, and we have just completed the linear momentum balance along x direction. And of course, similarly along y and z directions, we can write down the differential linear momentum balance as shown. Thank you, and we'll continue take it forward in the next lecture.